Welcome back to the CEE222 recitation for the week 9, and hopefully you have a great spring break. So let's start with the first question, 6.3.1. In this question, the question asks us to derive the relationship between the depth of the flow and the width of the rectangle channel that is most hydrologically efficient. So we have a channel, look like this is a rectangle channel, and we define the width of the channel to be B and the height of the channel to the water surface is equal to Y. So we can write down two different things. One is the area of this cross section will equal to B times Y, and the weighted parameter P is equal to A divided by Y plus 2Y, because you have Y here, so that is 2Y. And the B here is equal to A divided by Y, the area divided by Y, okay? So let me just write down P here. So if we plug these, if we move, we use this equation to know that B is equal to A divided by Y, and we plug these two here, then you will got this equation. Okay, so in the next step, we want to know what is the what does it mean the hydrologically efficient. So if you look at the main equation, we know that Q is proportional to something like this. Proportion to the 1 over P to the power of 2 over 3. So we know that given, if we want to maximize the flow rate, given the area of this cross-section channel, then what we want to do is to minimize this P, because this P have this relationship with the flow rate, as I show here. So next step, we want to maximize the flow rate for a given area, which is this A, and the idea is that we try to minimize P. Okay, so to do that, we need to calculate the differentiate of this P. So we calculate this dP2 over dy, and if you expand that, we will get minus A over y to the power 2 plus 2 from this equation, okay? And because we want to minimize these, and we know this so we know this equation should be equal to 0, because if we have a curve look like this, if you want to find the point here, it should have the derivative of to be 0, because the slope here should be 0. Okay, that's just the idea of the calculus, but I think you should know this. So if we have this relationship here, we can calculate the y of given area, and we know that the area is equal to b times y, as we show up here. So if we plug this back to this equation, we will get minus b times y divided by y squared plus 2 equal to 0. So now we have the relationship between this width and the height of this channel. That is, cancel this out first. So we will have the relationship that b is equal to 2y. So if the channel have satisfied this relationship I show here, then it's the most efficient channel that we can get given the rectangle channel with the area equal to A. So this is our final solution for this problem. Okay, now let's move on to the next one. The problem 6.3.4. In this problem, it asks us that if we have a concrete open channel, it's required to pass a flow rate 42.5. Design the best hydraulic section for the channel. Okay, so it's similar idea to the previous question. However, here we have the trapezoidal section. Okay, so let's start with this. So because this is a concrete open channel, and this concrete means that the n value for the Manning equation is equal to 0.013. Okay, and we have a flow rate equal to 42.5 cubic meter per second. So from the example in the textbook 6.4, we know the n value is 1/2 divided by 3, which is equal to 0.577. And because now we have a trapezoidal, okay, let me redraw this a little bit. Trapezoidal channel. So also from textbook, the B is equal to 2/3 times 3 times y, which is equal to 1.15 y. And now let's apply the table 6.1 from the textbook. We can't use the equation for the area for this trapezoidal section of the channel, which the area is equal to b plus n times y times y. In this case, let's just plug in the value, which is look like this. And we can get the final. Just organize this numbers together, then we will have the area equal to 1.73 square y. And similarly, we can apply the equation from the table 6.1 for the weighted perimeter. That's the P is equal to B plus 2y times 1 plus m squared to the power of 1 over 2. And let's plug in the number. Okay, and similarly, let's reorganize all those numbers together, and we can get that the P will equal to 3.46 y. Okay. So the base hydrological section for the channel, that means we want to maximize the flow rate. So let's apply the Manning equation. Manning equation here. That's Q is equal to 1 over n A to the power of 5 over 3 times the weighted perimeter, which is minus 2 over 3 times the slope to the power of 1 over 2. And let's plug all these values into here. And we assume the slope is equal to 0.01. Okay. And we also know that the flow rate is equal to 42.5. Okay. So let me rewrite this equation with all those information plugged in. So the Q is 42.5. And the N value, because it's a concrete channel, so it's equal to 0.013 times A, which is 1.73 y squared to the power of 5 over 3. And for the weighted perimeter perimeter is 3.46 y to the power of minus 2 over 3. And the slope, our assumption is 0.01, so I just put that number here. And this is to the power of 1 over 2. Then we can solve the y, the normal depth in this channel, by using this equation. And here I just provide you the number for y. Let me write down one more step for you. So if you organize this equation, you can get a simple form that y to the power of 8 over 3 will equal to 5.07, and you use this equation to solve y, which is also known as the normal depth of the channel. That is equal to 1.84 meter. And since we since we have this relationship here, that's B is equal to 1.15y. So we can also calculate the B, the width of this trapezoidal channel. That's 1.5y, where sorry, let me erase this, which is equal to 2.12 meter in this case. Okay, so we solve the y and the depth of the water and the width of the channel for this problem. And to see why we have this relationship, I highly recommend you to go to the example 6.4 to see the proof for why that with this M and this B, that a channel can be the highest hydrologically efficient. Okay, so in this problem, we just apply the result from the example 6.4 to and the Manning equation to solve the normal depth yn and the width b. Okay, so now let's look at the problem 6.4.2. So in this problem, we want to determine the flow, whether the flow is subcritical, critical, or supercritical using the two different methods. One is the flow number, and one is to calculate the critical depth and compare with the normal depth of the flow to see, compare to the depth of the current flow in the channel to see whether it is a supercritical flow or the subcritical flow. And this problem asks us to use these two different methods to classify the flow condition with this setting. So let's just write down the setting first. So it says that we have a rectangle irrigation channel with the flow rate equal to 25.3 cubic meter per second, and we have the normal depth. The flow in this rectangle channel is equal to the normal depth, which is this yn, that is 1.2 meter. And for this channel is 3 meter width. So this width is B. So B is equal to 3 meter. Okay, so let's first apply the method A, which is the flow number. And the equation for the flow number is, look at this, the velocity divided by g and the depth to the power of 1 over 2. Okay, so for the rectangle channel, we know the area is equal to B times yn, because we have the, let me erase this, the depth to be yn, so the area is B times yn, and this is 3.6 because yn is 1.2, B is 3, so you just times these two together, you get the 3.6 square meter. Okay, and we know that the flow, the velocity in that channel will be equal to the flow rate divided by the area. So it's 25.3, wait, 25.3 divided by 3.6, and this gives us 7.03 meter per second. Okay, so we now have everything that we need for this equation to calculate the flow number, and we just plug in a number. This is 7.03 divided by G is 9.81, D the depth is this YN, which is 1.2 meter to the power of 102. Then we will get the flow number is equal to 2.05 and it's greater than 1. So from the problem here, it tells us if the flow number is greater than 1, then this flow is super critical. Okay, so that's very straightforward. Okay, now let's apply the second method to calculate the critical depths and compare with this YN that we have here to see to classify the flow. So the the equation for the critical flow is looked like this: Q squared divided by GB squared to the power of 1/3. So similarly, we can just plug in the value here, and we can get 3 to the power of 2 divided by 9.81. B is equal to 3, so we times 3 squared and to the power of 1/3. Then you can get a value equal to 1.94 meter. And we found that this YC is greater than YN. So if we have the channel look like this is the normal depth, and we have a critical depth higher than this. So this tells us that the flow in the channel is also super critical. Okay, so in this problem we use these two different methods to classify the flow in the channel. One is use the flow number, which you just plug all those information into the equation that I show here. Then you can compare where the flow number is greater than 1 or less than 1. Then you can classify the number, classify the flow into supercritical or subcritical flow. And similarly, we have the equation for this critical depth. And if you calculate that, then you can compare the current depth the current flow depth in the channel, and to see whether this is supercritical or subcritical. Okay. Now let's move on to next question, 6.4.4. So in this problem, we have a rectangular channel to convey the flow with the flow rate equal to 834 CFAs in a 10 feet wide rectangular channel. So let me just draw the diagram for that. We have the width, which is B is equal to 10 feet with the channel, and this is the surface of the flow. This is Y. Okay. Where the Y is equal to 6 feet in this case. as the problem showed us. And the question asks us, what is a specific energy? So we want to solve the specific energy of the channel. And the second question is that is this flow subcritical or supercritical? Okay. The third one is that if the n is equal to 0.014, what channel slope must be provided to produce a uniform flow at these depths? So when it comes to the uniform flows, that means we want to solve these normal depth for the channel. Okay, so after we know what we want to solve, we can start to solve it. So in order to identify whether this flow is critical, is subcritical or supercritical, we just provide two different options in the previous problem. One is to calculate the Froude number, and the other way is to calculate the critical depth, and to compare with the current depth that we have for this channel. And here, let's use the Froude number to classify the flow. So the Froude number, the equation for the Froude number is V divided by GD 1/2, right? So the V is equal to Q divided by the area, and it's also equal, the area is B times Y, so B times Y, and we have all these value that we need to calculate the velocity. So we just plug in the value, then we can get the velocity is 13.9 feet per second. Okay, so we plug that into this equation. That's V is equal to 13.9, and G for the English unit is 32.2 times the depth, which is 6 feet, here to the power of 1/2. Then we found that the Froude number is equal to 1. So the Froude number equal to 1 means that the flow in this channel is critical flow. Which y equal to y equal to 6 feet, and this 6 feet is also equal to the critical depth for this channel. Okay, and that back to calculate the specific energy for that, and the equation for the specific energy is the velocity term plus the y, and you can just plug in a number. We already calculate that the velocity is equal to 13.9 and square divided by 2 times 32.2. Then you plus y again, which is 6. Then we have the specific energy number equal to 9 feet. Okay. So the remaining part is that we want to calculate the slope that the flow in this channel is uniform flow. To do that, we will need the Manning equation. That's the Q, the flow rate, is equal to 1.49 divided by N times A to the power of 5/3 times the weighted perimeter to the power of -2/3 times slope to the power of 1/2. Okay, so currently we have the area is B times area is B times Y. Perimeter front is 2Y plus B, and this is the number that the variable that we try to solve. N is 0.014, and we have a flow rate equal to 834. Okay, and you know B is 10 feet, Y is 6, B is 10 feet. So basically you have all the numbers that you need to calculate to plug in this equation, and the only unknown variable is this slope. So you use this equation, then you can solve that the slope is equal to 0.00448. Okay, so that just do the quick review for this problem. So we need the question asks us to identify to classify the flow in this channel, which we use the Froude number, and the Froude number that we calculate is equal to 1, so it tells us it's a critical flow. Then we can use the equation for the specific energy, and we just plug in the value. Then we can calculate the specific energy is equal to 9 feet, and to calculate the slope for that can produce such uniform flow, which means is the normal depth that we want to calculate. We use the main equations that I show down here, and we just plug in the number and solve the only unknown variable, which is the slope. Then the slope is shown down here. Okay, that is how you solve this problem. Okay, so this is the final question for this week, 6.4.10. And the question is that we have a hydrologic transition 100 feet long is used to connect two rectangle channel. One is 12 feet wide and the other one is 6 feet wide. So let's draw the diagram for that. We have a channel. If we view the channel from the top, we can see something like this. So originally the channel is 12 feet wide, and later it shrank down to 6 feet wide. And the transection area is 100 feet long. And we have the designed discharge is equal to 500 CFAs. The main coefficient N is 0.013. I guess that is because of the concrete channel. And also it gave us the slope of the channel is 0.0009. Okay, in both of the channel, that's we have the same slope. Okay, and it says that during this transition, the energy loss is equal to 1.5 feet, and we have a uniform distributed throughout the transition things, and assume the uniform depths, the normal depths, before and after the transition. Okay, we want to solve the change in the bottom elevation and the water surface profile to satisfy this condition. Okay, so to do that, because it already tells us, we assume the uniform depth before and after a transition. So we try. The first thing that we need to do is to calculate the normal depth for this wider channel and this smaller channel, and that just give a notation that's for this wider channel we have the normal depth wider than 1, and for this smaller channel we have the normal depth equal to yn2. Okay, and to solve that we will need to use the Mann equation to solve the normal depth. That's we write down the Mann equation that is equal to the flow is equal to 1.49 divided by n times a to the power of 5 over 3 p minus 2 3, and finally the slope to the power of 1 over 2. Okay, and because this is a rectangular channel, so we know that the area is equal to the water depth times y times b, sorry, and the weighted perimeter is equal to 2y plus b. Okay, so basically this y here is the normal depth that we want to solve. So for the wider channel, which the b is equal to 12 feet, we plug in a number that the flow rate is equal to 509 divided by 0.013, and we have this n1 times b, which is 12 feet, to the power of 5 over 3, and we times the perimeter from no why I keep saying that, the weighted perimeter, 2 times y, and just yn 1 plus 12, and we have the slope 0.0009, and you can use this to solve the yn using your calculator. And here I just give you the number, that's yn1 is 5.88 feet. And similarly, for the width equal to 6 feet, we have a really similar equation. Look like this. The only difference is that the width now is changed to 6 feet to the power of 3 to yn2 plus 6. Okay, then again use your calculator to solve this equation. You can get yn2 is equal to 13.4 feet. Okay. Now we want to calculate why is the bottom elevation change to satisfy the uniform flow condition that states in the problem. So we need to use the energy balance to solve this equation. So basically the idea is that let's start another section here. The idea is that if we use the energy balance, the entrance of this transition flow have the energy HI will equal to the energy on the axis plus the angle that we have here, which is 1.5 feet that given by the problem. So let's expand this equation. First is the velocity term plus yi plus zi. Zi is the elevation for the entrance channel, should equal to velocity term for the axis plus ye plus ce plus hl. Okay, so let's assume that the elevation of the axis is our datum, so this is equal to 0. So the delta z is equal to zi minus zi, because this is 0. Okay, that's the things that we'll try to solve. And we know the depth, the normal depth for the wider channel and the smaller channel, and we also know the flow rate. So we know the Vi is equal to Q divided by Yn1. That is 7.09, and VE is Q divided by Yn2, and we have all those values show above. That is equal to 6.23. Okay, so now we have this velocity. You can just plug the number in, and we also know this yi, because this yi is Yn1, this ye is Yn2, and we know this angle is equal to 1.5 feet. So you can solve that the delta z, the elevation change, will equal to zi is equal to 8.84 feet. So if we look this channel from the side, and let me erase this a bit. Okay, so this is the transition section, and if we look this transection section from the side, we have an elevation look like this. Okay, so here is 0, and here is 8.84. Okay, so that's answer the first sub-problem here. But the second thing is that we want to solve the water surface profile. And that means we need to solve the water depth for this channel, transition channel here. To do that, we can write down in a table as I show here, and let's just find some points during this transaction section. So here we have the inlet, and we have the different distance from the inlet, 25, 50, 75, and finally the axis is the 100 feet part. And because the question that we have the linear change of the width, so we can write down this width for the transaction channel to have a linear decreasing value from 12 to 6. And because we also solved that the elevation change is equal to 8.84, and it's also linearly decrease to from the inlet to the axis, so we can also calculate this value for the z. Okay, so this is known, this is known, this is known, and the energy loss 1.5 is also linearly added to this transaction channel, so this is also a known value. Then you can solve this specific energy by H minus Z. So basically it's this value minus this value. Okay, then you can get the specific energy, because we have a specific the energy is V divided by R2G plus Y plus C. So this is the specific energy, E. Okay, so to calculate E, you just need the energy, the total energy minus the elevation elevation term. Okay, so this is also known. So finally, we can use all those information to calculate the water depth across this section in the channel. And to do that, we know that the specific energy is equal to V G plus Y, and we can replace the velocity term with this Q divided by 2G B Y plus Y. Why? Because V is equal to the flow rate divided by the area, and area for the channel, the rectangular channel, is By, right? So we just plug, we plug this V to this equation here, then we got this one. And you can plug the B from this column, and the flow rate is a fixed value that is equal to 500. It is 500. And we also know the E, the specific energy. So the only unknown variable is the water depth, this Y here. So you can just solve this Y for different distance. Then you got the final corner of this table show here. And you can plot this profile onto the figure here. Then you got the water surface profile, because you still need to add this datum, I mean the elevation, to the flow depth that you solve using the specific energy. So you need to add this elevation here. Then you will get the final water surface profile for this transition section. Okay, so that's, again, do a really quick review. In this problem, we first solve the normal depth using the main equation for the inlet and outlet. Okay, and we got this yn1 and yn2. Then we use the energy balance to solve the elevation change, this delta Z, in this transition section. After that, we interpolate those transition in the width as well as the elevation change. Then we use this specific energy equation to solve the flow depth across this transition channel. Then we just need to plot the elevation Z and the flow depth together to be able to calculate the profile for the water surface. Okay. So yeah, that's it. This is the last question for this week's recitation. See you.